Welcome to a lesson on differentials for functions of two variables. In Calculus 1, we learned that for functions of one variables, differential y, or dy, was equal to f prime of x times dx. Well, for functions of two variables, meaning z is defined in terms of x and y are going to be independent variables. Therefore, differential z, sometimes referred to as total differential, is going to be equal to the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. And of course we can use this notation here if we wish. And remember, differential z can be used to approximate the true change in z when the values of x and y change. To get a better feel for this, what we're going to do is compare delta z, the true change in the function, to differential z, the approximate change in the function, when x changes from 3 to 3.1 and y changes from 4 to 4.3. So let's first calculate the true change in the function value, and then we'll determine differential z. The true change in z is going to be equal to f of 3.1 comma 4.3 minus f of 3 comma 4. So we're going to take x equals 3.1 and y equals 4.3 and sub it into our function, as well as x equals 3 and y equals 4. To save some time, I've already done these calculations. This comes out to approximately 5.3009. This ends up being the square root of 25, which is equal to 5. So the true change in the function value is 3.009. And what we're going to do is calculate differential z and then compare differential z to delta z. Let's go ahead and do that on the next slide. Notice to determine differential z, we're going to need the partial derivative of the function with respect to x and with respect to y. So let's go ahead and determine these partial derivatives first. But before we do that, I'm going to go ahead and rewrite this as the quantity x squared plus y squared raised to the 1/2 power. So now let's go ahead and determine the partial derivatives with respect to x and then with respect to y. So the partial of z with respect to x is going to be equal to 1/2 x squared plus y squared to the negative 1/2 times the derivative of x squared plus y squared with respect to x, treating y as a constant, so that would be 2x. Let's go ahead and simplify this. So the 2's simplify out. So we're going to have x. Let's go ahead and move this down to the denominator. It's going to be the square root of x squared plus y squared. Now let's find the partial of z with respect to y. So it's going to be 1/2 x squared plus y squared to the negative 1/2, and now it's going to be times 2y. Simplifies in a similar way. So we have y divided by the square root of x squared plus y squared. In order to calculate differential z, we're going to have to determine dx and dy as well. Looking at the problem here, notice that x changes from 3 to 3.1. It's increasing. So that tells us that differential x is going to be equal to positive 0.1. And for differential y, y increases from 4 to 4.3. So differential y would be 0.3. And also x is equal to 3 and y is equal to 4. So let's go ahead and determine differential z. It's going to be equal to the partial with respect to x here times dx. Remember, x and y are 3 and 4, so we're going to have 3 all over the square root of 3 squared plus 4 squared. Well, that's going to be the square root of 25, so we have 3/5 times dx. Well, dx is 0.1 or 1/10. We'll write it as 1/10 plus. Now we'll evaluate the partial derivative with respect to y at the 0.34. So now our numerator is going to be 4. Our denominator is going to be the square root of 25, or 5. So now we have 4/5 times differential y, which is 0.3 or 3/10. Let's go ahead and evaluate this. So we're going to have 3/50 plus 12/50. Well, that's 15/50. If we simplify this, we're going to have 3/10. So differential z is equal to 0.3. This is a very good approximation of the true change in the function given this change in x and this change in y. To go back to the previous screen, the actual function value change was 0.3009. So again, the idea here is that differentials can make a good approximation of the change in a function. We'll take a look at some more applications of differentials in another video. Let's go ahead and get a little more practice finding total differential, or dz. So again, I think it's often helpful to first find the partial derivatives before we fill out the complete formula for differential z. So let's go ahead and do that. The partial derivative of f with respect to x, treating y as a constant, notice both of these functions have x in them, so we'll have to apply the product rule. So we'll have the first times the derivative of sine 2x, that's going to be cosine 2x times 2, plus the second, which is sine 2x, times the derivative of e to the xy with respect to x, treating y as a constant. So we'll have e to the xy times y. Let's go ahead and clean this up. So we'll have 2 e to the xy cosine 2x plus y e to the xy sine 2x. So for the partial derivative with respects to y, remember x is a constant, so sine 2x would be a constant. So we'd have e to the xy sine 2x times the derivative of xy with respects to y, so that would be x. Let's go ahead and rewrite this. This would be x e to the xy sine 2x. Okay, that's all we need in order to determine the total differential. Differential z is going to be equal to the partial with respects to x times dx plus the partial with respects to y times dy. And that'll do it for this video. As I mentioned before, in the next video we'll take a look at a couple application problems involving differentials. I hope you found this helpful.